So I mentioned like the impedance of getting out of the flow of energy getting out or momentum moving. So let's actually develop a quick little model here, an approximate model for these. So if I'm energy on the surface, I have to get out to free stream. And I want to characterize this in terms of a resistance model, which we've done before. The resistance model is going to look something like this. I would have here at the surface, this is TS. Out here at the edge of the boundary layer, this is going to be T infinity. And then there's basically a thermal resistance that's in there, right? And it's just this resistor here. This resistor is going to be delta T, let's see, delta T in the laminar region, the thermal boundary layer in the laminar region, divided by the conductivity. That's our resistance there. Okay, and if I go through and write out heat flux in terms of that, so Q dot double prime S, that would be approximately Ts minus T infinity divided by that resistance, which is delta T laminar over K. Okay, and that's, again, we kind of define that as H laminar Ts minus T infinity. That's our Newton's law of cooling for laminar flow. Easy enough. We just have the one resistance. For turbulent flow, though, we now have to think about the two things. We have to think about our viscous sublayer, and we have to think about the turbulent or eddy regime. So we have basically now two resistances, right? We have a resistance to get from here Ts to some intermediate temperature at the edge of the boundary layer, and then out here are the viscous sublayer, and then out here, this is T infinity, right? So now we have two resistances that we have to care about, both in series. That thing on the bottom is a resistance, right? So if we write this out, a rate equation for this would be Q dot double prime, Q dot double prime S in the turbulent region is going to be approximately equal to Ts minus T infinity divided by what's going to be the resistance here. Well, we have, again, two resistances in series. The first one is the viscous sublayer, delta Vs, divided by, now what's conductivity, but which conductivity is this going to be? Is it going to be my effective conductivity, or is it going to be the molecular conductivity? Anyone know? The first, the viscous sublayer. Molecular, right? Because it's laminar flow there. The only mechanism for heat transfer in the viscous sublayer is conduction, right? Not bulk fluid motion. So this is just going to be plain old K. Okay, and then the second resistance is in series with that is going to be delta T turbulent divided by now my conductivity, my effective conductivity in the turbulent region. If I were to be very particular, I could say this is actually delta T turbulent minus delta Vs, but it turns out that delta Vs is so small compared to delta T, as long as we're doing an approximate model, it's basically the same thing as delta T. Okay, so the other thing we want to remember is, what did we say before? That K turbulent is much greater than K. So if that's the case, although delta Vs is smaller than delta T turbulent, K turbulent is so much bigger than K that we can essentially ignore, in our approximate model, we can essentially ignore this second resistance entirely. Right, so then we can write this equation as follows. K double prime S turbulent is approximately equal to Ts minus T infinity divided by delta Vs over K. So this is a good approximation for our heat transfer in the turbulent region, and it only depends on the viscous sublayer. So when you go through and you're using correlations, which we'll do for this later on, correlations for turbulent flow, those turbulent flow correlations are often written for the viscous sublayer. Right? You are basically solving for the viscous sublayer thickness in the correlation and doing the heat transfer calculations that way. Those are written in something called inner coordinates. So we'll get to that in a lecture or two, I think. But for now, this conceptual understanding is good enough. So the last thing here is H turbulent then is approximately delta Vs over K, molecular diffusivity K. molecular conductivity. Okay. Okay. Let's see. Some of this is hopefully not beating a dead horse too much, but let's talk about the heat transfer coefficient and the shear stress and how they behave really quickly. So let's draw our flow again. So flow over the plate coming in this way. So if I were to draw let's say this is our, let's label this. So here we have this being x critical here. So this is going to be laminar. This is going to be turbulent. And this in the middle is going to be our transition region. So if I draw the heat transfer coefficient, let's say first, let's draw heat transfer coefficient as a function of this position on the plate. It's a function of x. That's going to look something like, well, we know what it's going to look like for laminar, right? We start off really high and it goes down as we go in here. As we start getting into this transition region, though, what's going to happen? Well, think about, right, we're starting to form a viscous sublayer, and then you're starting to get bulk fluid motion in the y direction. There's a transition between the laminar region where none of that's happening and the turbulent region where all of that's happening. And kind of in the middle, you get this kind of weird transition state. So it's going to actually start breaking up that laminar layer, and you start getting flow, start getting flow in the y direction. So you start growing again. Okay, and eventually we get up to this turbulent region up here, and then that viscous sublayer starts forming. And remember, I drew it where the viscous sublayer starts off really small, and then will eventually very, very slightly grow as a function of position. So the turbulent heat transfer coefficient is going to do something like this as that layer grows. So this is our H as a function of X. So if I'm designing, and keep in mind this isn't to scale, right? So I'm a heat exchanger manufacturer. Am I going to want my heat exchanger to operate in the laminar region or in the turbulent region? Turbulent. Because on average, in the turbulent region, you're going to have much better heat transfer coefficient. If I'm the guy making the pump for that, would I prefer laminar or turbulent? Laminar, right? So you're always fighting against those two things. Right? The same thing's happening here. We could draw tau. Right? So tau is going to be like this. You get an increase in shear stress. It's doing exactly the same thing. This is tau. Right. So yeah, there's always this balance. Typically for heat exchanger applications, people tend to care more about the heat transfer coefficient than the shear stress. So they will often operate in that turbulent region. And if the flow is not sufficient and not sufficiently high velocity to create turbulence, you'll introduce turbulence through surface features, which can happen. Okay, so then last thing here, let's just quick sketch out, making sure we understand what the temperature profiles look like in these two regions. So let's pick a couple locations here. Here's our locations that we're going to plot out. Let's sketch the temperature profile, keeping in mind that, let's draw a little viscous sublayer here. So I'm going to make it a little bigger than it normally would. So in the laminar region, we kind of know what the temperature profile looks like. We have, let's say at our surface, I'll draw it in green here. Maybe let's use red. So red on the surface, here's our TS. We know at the edge of the boundary layer, we have to have T infinity, right? This being T infinity out here. And they're connected nicely like this. And then out here we have constant temperature T infinity. So that should be pretty familiar to you. What's the turbulent region going to look like? So again, we have TS, we're enforcing TS out here. We know out here at the edge of the turbulent boundary layer, we have T infinity. So we just decided that we could basically neglect the entire resistance between the edge of the viscous sublayer and the edge of the turbulent boundary layer. So what's my temperature profile going to do? Right? It's going to go something like this. So if I was being really careful and could draw without making squiggly lines, you'd see that it goes right up next to the T infinity temperature, but it's not quite. There's still actually a little bit of a temperature difference, and that's resolved through the rest of the boundary layer. And again, this is going to be your average temperature.